Hi everyone, thanks for attending this session. My name is Arash. I'm a PhD student of mechanical engineering here at Purdue. Today I'm going to talk about our study, which is titled as What Have We Learned from Field Demonstrations of Advanced Commercial HVAC Control. Before diving into the contents, I would like to acknowledge the help and support of my colleagues, Elias Pergantis, Levi Premier, Alex Lee, Dr. Jima, Dr. Hati and Leo, Professor Gregor Hanza, and Professor Kevin Kircher. So, as we know, residential and commercial sectors account for almost 29% of energy usage in the United States, with half of that utilized for thermal comfort using heating, ventilating, and air conditioning systems. Advanced control systems can significantly improve energy efficiency and occupant comfort. Many studies over the last 2 decades claim that advanced controls such as model predictive control or MPC, reinforcement learning or RLC, and carefully designed rule-based controllers or RPCs can achieve some or all of these objectives. However, there are a few papers that have demonstrated this potential using hardware and actual real-world studies. So we don't know whether or how these are accurate or not. Most of these studies up until now have been simulations. Having said that, we have done an exhaustive search of multiple indexing services such as Google Scholar, Scopus, IEEE, and other services to find out the exact number of these papers. As can be seen from this pie chart here, the distribution of the papers are being shown. Almost 78% or around 2,000 papers since 1997 report model predictive control. Almost about 20% of these papers, around 500 papers, report reinforcement learning control, and only around 2% of these papers, or around 50 papers, study field demonstrations of advanced commercial HVAC control since 2005. Within this small subset of papers, there's lots of variability in the methods that authors are using, in the building types, in the equipment type, and even in the savings that authors report. For instance, some papers report no savings at all, or some papers report 80% of energy savings, and there are other papers which is in between. Therefore, we are doing this review study to understand which factors are the most contributing ones, and trying to understand those factors that basically lead to higher savings or lower savings in this kind of papers. So there have been a large number of big picture review papers to date that describe how and why to perform supervisory control of HVAC systems. However, there have been a few partial review of field demonstrations that typically are reporting portions of other things in their papers, such as their own control demonstrations. The first paper was from David Sturzenegger in 2016, led by Professor Manfred Morari in ETH Zurich, which that time was a comprehensive review of field demonstrations of MPC for HVAC in commercial buildings. A more recent study in 2022, led by Dave Blum and other collaborators in Lawrence Berkeley National Lab, showed that there are other papers which report field demonstrations of MPC in commercial building HVAC systems. On the residential side, Elias Pergantis, my colleague led by Kevin Kircher here at Purdue, reported the field demonstrations of advanced supervisory control in residential buildings. Here in our study, we are reviewing 36 papers, which essentially focuses on 56 tests, and our focus will be on commercial buildings. We are analyzing test durations, building types, control methods, objectives, and other reported improvements in these papers. We would like to focus on lessons learned during this analysis. The first lesson is controlling a subset of building seems to overestimate savings. The second lesson is longer, larger experiments suggest lower savings. And the last lesson that we learned is very few studies address deployment cost challenges. Therefore, there is a need for more studies showing these deployment cost challenges and labor efforts. With regards to the methodology, we populated this very large spreadsheet that has many rows for the papers that we studied, and there are many columns other than the columns that are being shown as a sample here, which stand for different characteristics of a control experiment. Here, I'm not trying to draw your attention to the spreadsheet. I just want to focus on how we explain, how we basically did this research here. We performed a rigorous search of different indexing services, as mentioned before, such as Google Scholar, Scopus, and IEEE. We used different keywords such as practical implementation, experimental study, commercial building, model predictive control, MPC, reinforcement learning control, RLC, and HVAC. Additionally, we examined the citation network of different papers, conference papers, journal papers, and other important theses to kind of understand which of these papers are field studies and which of these papers have been cited by the other papers. By the way, if you would like to see the raw data contained in this spreadsheet and even conduct your own analysis, you're more than welcome to do so. By scanning this QR code, you will be directed to our GitHub repository, which includes all these raw data for this experiment that we've conducted. So as discussed, multiple characteristics define a supervisory commercial HVAC control experiment. To optimize the space in our paper, we have reported control methods, building type and location, test duration, objectives, and objective improvements. Even within this small subset of papers, we can see that there are lots and lots of variations. For example, with regards to the objective improvement, we can see that the for example, the objective improvement ranges from 8.3% up to 35%. Or in terms of the test duration, test period, we can see that we have a test for 1 day and we have a test for 3 months. So we don't know which factor is more contributing to the objective improvement. With regards to this figure, this basically illustrates the yearly cumulative number of MPC, RLC, and total papers published and tests conducted since 2005. And as can be seen, here in this graph, the dashed lines show basically the number of tests, and the solid lines basically show the number of papers. The x-axis stands for the year, and the y-axis stands for the cumulative count. As can be seen, the data show a gradual increase in the number of experimental MPC studies during these years. On the other hand, on the RLC research side, we can see that the first RLC paper has done nearly 15 years ago in Professor Gregor Hansa's group, and this only experienced significant growth only after 2020, which corresponds to rapid developments in AI and RL research. This surge in RLC suggests a growing interest, likely due to increasing awareness of its potential in different industrial applications. In order to report the savings, we use duration average method. So our first lesson mentions that controlling a subset of buildings seems to overestimate savings. To calculate duration weighted average here, it's critical to identify the key features of the supervisory control experiment. Among many characteristics, as we mentioned before, here we are focusing on the control spaces scope, whether it's a subset of a building, whether it's 1 zone or 2 zones in a building, or whether it's a whole building study. And we came to conclusion that the number of studies in both categories is not the same, but they're almost equal, 33 versus 23, which gives us a good sense of comparing these two studies. The left figure basically shows a bar graph which compares the number of studies. On the other hand, we have this right figure, which is basically the result of this analysis. The x-axis shows the control spaces scope, whether it's a subset of a building or whether it's the whole building, and the y-axis shows energy savings in terms of the duration weighted average savings. For subset of building, we report 26%, almost 26% of energy savings. But for the whole building study, we can see this is around 30%, which is half of the reported number for subset of building. This analysis basically suggests that focusing control measures on a specific subset of building can be more effective in terms of energy savings. This is something that's evident from the figure. However, we think that these higher savings correspond to some other things that are being happened in our control experiment, such as the energy flow between different zones, whether there's energy leakage between the different zones or thermal interactions in our zones. For example, if I'm only controlling one office in a large building and I raise the temperature of the room by a few degrees, for example, I'll lose less energy through the office window, but gain some through cooling, through conduction from other zones. So therefore, we can conclude that there is energy leakage, and some of these authors are not basically reporting these energy leakages or thermal couplings in their studies for subset of building studies. Therefore, it yields in more energy savings when compared to whole building studies. The second lesson is longer, larger experiments suggest lower savings and less uncertainty. These two figures demonstrate duration weighted average of energy and cost savings versus test duration for the left figure, we can see from the x-axis, and the floor space, in terms of the floor space, we can see in the right figure. There are three key messages from these figures. There seems to be lower number of large number and longer number tests. So basically, our large scale and long scale studies are not too much in the literature. We can see it from these, basically these points in the right side of these figures. The second message is there is a downward trend in both figures as the test duration gets longer and as our building gets larger and the building size increases, there is a downward trend, and we can see that the savings gets lowered. And the third message is the noise in the estimates, or basically the spread of estimates or randomness is enormous, ranging from 0 to 18% at the lower end of the test duration or a small spatial scale. So for example, we can see that a one-day study or a one-room study is not that informative in terms of the energy savings. Therefore, when the spatial or temporal scale is low, the variability and randomness will be higher. There is need for more studies addressing deployment costs and challenges. So among 36 papers that we have discovered and studied here, only 6 papers report these deployment costs and challenges. There are a few field demonstration studies that have adequately addressed these labor costs and deployment challenges. So initial papers in the field are mostly reporting benefits as compared to scalability analysis because of the novelty of research, limited Internet of Things infrastructure, and the need for many researchers to create their own weather models. However, we can observe that since David Sturzenegger in 2016, other studies have contributed to this challenge, namely Kim and Brown 2018, Granderson and collaborators 2018, Blum et al. 2022, Han 2023 and 2024. Most of these studies are from ETH Zurich, Purdue University, and Lawrence Berkeley National Laboratories. To conclude the talk, controlling the subset of a building seems to overestimate savings. Longer, larger experiments suggest lower savings. There is a need for more studies which address these deployment costs, labor efforts, and challenges associated with those. And in terms of the future directions, we would like to include the remaining portion of commercial papers. We're not 100% sure that the papers at this time are 36. It could be increased in near future. We would also like to include the remaining portion of residential building studies with the ones that also Elias Pergantis 2023 studied. We would like to explore other interesting trends such as uncertainty quantification, measurement and verification methods, and so forth. And importance of addressing deployment challenges and costs are inevitable. Thank you for your time.
Okay, maybe our second speaker could come down and we could set you up on the mic. And then while we're doing that, is there a question maybe from in the room or online?
Yeah, can you go to slide 7? I guess it's really, the question is really the higher savings for a subset of buildings, right? So is this because when you look at the whole building, you've got certain, loads that are not really available for control, like, lights and computers and equipment, things that are sort of programmed in and they're not part of what's available, or is it something else, right?
So good question, thank you. We think it's something else. And so to be super concrete about that, if we controlled only this zone, and suppose we're in cooling mode, we might, in MPC or RLC, raise the temperature of this zone by a few degrees. Okay, and then if we're measuring energy consumption, say thermal energy provided only at the zone level, we would miss heat transfer between this zone and adjacent zones. We think it's almost exclusively that effect. So there are fictitious energy losses that aren't accounted for. Yeah.